Hello everyone. So my name is Floris, and I'll be talking a little bit. So the talk says I'm going to talk about Conda. That's kind of a little bit alike. I'll be talking much more about shared libraries and linking, etc. And basically, kind of the reasoning why I think the way that Conda actions and the way you can distribute applications using Conda is the right approach to cross-platform distribution of your application. I won't actually be showing you any Conda commands or how you use Conda or anything like that. So if you were expecting that, I'm sorry, I won't be offended if you. It's all fairly Linux-centric. Conda supports Windows as well, but we haven't actually reached Windows support yet. When I say Linux-centric, it's kind of Unix-centric, so it's kind of all fair. The goal that I'm sort of trying to do here is just basically distributing your application, your product into a kind of customer kind of application. So that's kind of my primary concern, and the concern I have there is quite different, because you don't necessarily know the platform, or you don't have that type of control of the platform, and you also don't want to intrude in lots of random corners of the host system that you're on. And yet you need to be able to reliably run your application, whether it's on Red Hat 5 or on the latest Ubuntu version or whatever. But even if that isn't your target area, I think Conda is still quite interesting, because it's very cleanly separates build time, where you need compilers, etc., versus deploy time, which is which is basically fairly static for Conda. It just kind of unpacks the tarball essentially and moves around a few bits. You don't need any tool chain or anything like that. Nowadays, you can also achieve that quite well with Windows, I think, but I've never really used that. The last thing you can get, you can control the entire stack very, very nicely, which is also a good feature. So a little bit about my background, I guess, about why how I've come to do these things. I work for Kobe.io, and we've sort of been monitoring software. So we have to deploy agents to servers, and we've been doing Kobe.io software and our company has been doing monitoring for quite a long time now. And we've been shipping, and we have been doing this mostly using Python. And so we have been needing to ship Python applications that are the agents to do the monitoring. And during that, the problem with writing monitoring applications is that you basically goes to support eventually all platforms people can think want you to run things on. So it's a really important place to do it. So we've had to support things from Bruynooghe, Red Hat 3 to AX to Floris, etc. So it's, it can be quite powerful. Being able to reliably run your application and all those means you have to ship basically Python itself. That's the only way you're going to get reliable runtime. So before we get into a little bit more about Conda, I think I should just so everyone's kind of on the page what shared libraries are. So shared libraries are basically the basic approach to supplies this, and it's basically so you've got a library with so you've got a Bruynooghe application, so that's say Python, and it uses libraries that are very implementable independently. C Python uses like Zip and Readline, etc. And shared libraries are basically they give you a bunch of functions that you can call that are not part of your main binary. The way functions are identified is basically by symbols, which is essentially just a function. And when the library gets created, it basically builds a big list of, I provide all these symbols, this is my library. And when you're compiling your application, the linker at compile time, which is LD traditionally, is going to look at, so you're telling your compiler, I'm going to link against this library, so it's going to try and find this library and record the symbols that you need for it. And the idea is that instead of taking a code of that function and putting it in the binary, at runtime, you just go to at the runtime, the runtime function comes in, and instead of before you can run your application, so the way the runtime link works is kind of very similar to how you store a Python script. When you invoke your binary, you don't actually invoke the binary directly. So when you invoke Python script, you do hashbang Python, or use it in Python or something like that, and then the kernel will start Python up and will pass it your script file. The same actually happens with real applications. Your binaries actually start with a magic number, and the kernel reads that magic number and says, oh, I need to encode this using an interpreter, in this case, the runtime. Generally not even your part called SLE or so on Linux, SO2 these days. And that runtime link is basically responsible for creating all the memory layouts, and it looks at the symbols all the symbols that your binary needs. It will then try and find the library that's saved somewhere in a configuration file on the system usually. Try and find the library, and then it will try and match all the symbols of how you can go and use them. When it needs to find this library, there's normally there's default parts on your system that's in a configuration file, but you also sometimes that might not be the right location to find the library, and that's where in your binary you actually can encode an R path or also a run path, which are actually two different strings basically that you can tell the compiler to just stick into your binary, and they override the location. So you can actually say, instead of looking at normal use lib or whatever it is for the system, go and look at this location for my library. So the difference between R path and run path is essentially when it will go and look for it. So for R path, the link will look at the path you supply first, look for the library. If it's not there, it will go to it will look at the standard locations. Run path doesn't go around. It will go and look at standard locations first, and then look at the location you supply. So you can sort of provide a library if it's not available using that sort of feature. The last thing about shared libraries is basically it's kind of all those function calls that are in your shared object have a signature, just like Python functions have signatures, and they take particular types, etc. And they're called the API application binary interface, and they have to match. So if you compile your application on one host and then try and run it on Red Hat 7 and try and run Red Hat 4 or something, the API has to actually match for that to work. So in general, you can evolve the API a little bit without breaking already compiled applications. If you're very careful about how you extend your types, etc. So if you're having structures in Argon or something, I think you can safely extend the struct. And there's a couple of things that you can safely do. The downside is if you compile for that for the newer version and you try to run that binary on the old version, that's obviously still not going to work anymore. So that's kind of a background in very high review, to be honest, of shared libraries. And all those kind of semantics cause problems when trying to run your Python application, where you're trying to provide a Python binary onto an array of operating systems. So back to the problem actually of distributing your application to all these different systems. And the first thing there that you might be tempted to do is, well, most Linux distributions these days are provide a Python binary there, but I think it's actually kind of quite important to kind of recognize that system Python, your Linux distribution that you run might provide a Python binary, but that wasn't made for you. The only reason that they ship that Python binary is because the OS also happens to ship applications that use Python themselves, and the distributions will only make that Python because they need to run those applications that they want to support. The problem with trying to use that sort of system via Python is that if you're on all the versions of Python, you will have all, on all the versions of operating systems, you will get all the versions of Python, and then you have to write new grades for the denominator. You have all the extension modules may or may not be there, so you kind of have to restrict yourself or try and ship the length, at which point you actually have to ship it all the Python in a way once you start having to ship extension modules. Another reason that, so the other thing you can sort of do is try and ship your Python binary and try and rely on the system libraries as sort of what this runtime features kind of allow you to do a little bit. The nice kind of feature that would give you is that you might, one of the great features of shared libraries and why distributions, Linux distributions are so keen on using them, is because you have all the library code in one location, instead of spread around in everything. So it does a huge security thing. You only have to care about updating that one library, and you just need to restart the applications using it. So that's kind of a great feature. So if you lose that, that is kind of a little bit annoying. But on the other hand, if you do try and do that, your library, because of the API that I talked about, the library is kind of they're so different. So you can try and build on. So the solution there you can kind of try and do is you try and build on the oldest version that you want. You can try and build on the oldest version that you want to support, and then hopefully if they all behave correctly, they will provide you. They don't break the API unnecessarily, etc. That's a big if, to be honest. Then you might be able to get away with it. But if you have to support very old systems as well, they might just not have the right library at all or something like that. We actually did that for a while. That sort of works, but what we ended up doing is basically building for each and every operating system that we needed to support. So we could have one for Red Hat 3, Red Hat 4, Red Hat 5, etc. So that is a lot of builds basically. And another thing you do end up, a lot of things, something you do end up running into is, at some point you're going to want, so this is kind of the case with, I think we're into it with OpenSSL and security kind of libraries, where basically they just require features that are no longer, available on their systems, and sometimes you can't even use the compiler that is actually on this older system because it just can't compile the newer versions of Sodium or SSL. So you do eventually run into trouble there as well. Another thing that you end up doing there is you end up basically trying to deal with random old libraries that are kind of slightly different as well. So there's a lot of pain there as well. So what Conda does instead is basically you don't, it's basically you don't rely on any system libraries at all. Basically trying to compile everything from scratch yourself and distribute the whole thing. The way Conda manages this is fairly non-intrusive because you can build an entire system based on one directory tree, and this is using the RPAth feature. And Conda makes breaking a distribution like this fairly painless. I should say, this is kind of our approach to using Conda because if you actually dig down into last time I dig down into the mini Conda and Conda distributions that they make, they do still rely on more libraries in the system, especially near like the TK module depends on TK libraries, and they run X-Window libraries, and the upstream Conda and Anaconda, mini Conda and Anaconda distributions actually do end up relying still on some system libraries. We try to completely isolate that, so apart from libc, which we'll get back to, because that's a little bit more problematic, but that's also fine, that actually works. That's kind of what you try to achieve in Conda. And the way Conda's build system works, it actually takes care of most of these details. If you try to do this by hand, it's a little harder. Conda tries to help with that. So if you ever build any kind of applications, you probably going to configure, make install plans. And in general, you can pass minus prefix into that. And the way Conda does that is you basically, it gives you a build, it kind of creates an environment for you that's going to be a directory somewhere with everything self-contained. It installs all your dependencies there, and you just basically build it in that prefix, which is very natively supported by our systems. So that's kind of a fairly straightforward thing. And then after the build, basically, Conda will go through, will scan for the. So after the build, Conda will scan for all the files that you've added, and it will look at all the binaries you've been inserting in there, and it will replace it with RPath values, so that if you do redeploy it actually uses the libraries in your environment rather than accidentally going to the system of the libraries. To do this, they basically do some slightly more as well during install time. That's why it's slightly more than just the tarball. The problem with just unpacking tarball is that you stuck to where it was created. So if your prefix was, I don't know, /Conda or something, then you stuck to that prefix, and Conda tries to make it relocatable so you can install, so you can deploy your entire environment in wherever on the file system. And for that, basically, that's why they need to modify RPath at real time, and that's also, for that they also try and replace, they try and detect the prefix that you have to build at, and replace that. They also try and do that, well, optionally they try and do that for binaries. That's a little bit more dangerous for binaries because you can only make the prefix shorter, and you're kind of hoping that the null terminated string is kind of read as a null terminated string. So that's why it's optional and not enabled by default. So yeah, shortening, replacing prefixes in binaries is a little bit dangerous. Ideally, binaries don't do that sort of thing. Things like that, but it does happen. And I mentioned the libc exception. libc is actually a little bit more difficult. So libc, when you trying to build libc, it's actually feasible to all work, but it's also tied to your kernel quite a bit. So if you end up with libc, it's quite limited in what kernels that. Definitely on more modern kernels, that's achievable. I think Go does that because they started building the entire thing. I think Rust has been experimenting that as well using the Muslim library. And on newer kernels, that kind of works because it's fairly compatible. But if you're moving around a little further on kernel versions, it does become quite tight to it. So you can't really build libc that's going to work everywhere. And to make this worse, GCC is actually when you build GCC, which you do, you end up with GCC tries to kind of, and this they've been doing this because they run on random systems that are not Linux at all, and they have to deal with all sorts of problems. But the end of it is that they end up changing header files in libc as well, because they know better how they should look, and then they take them into GCC compiler. And you can't avoid using those headers anymore, even though the system actually supplies the correct ones, because libc is actually written quite well, glibc is at least. So if you end up, so the end of the result of this is if you end up building GCC on a particular version, you can't really move that to another host. So if you've been building GCC on Red Hat 5, you probably won't be able to compile your applications using that GCC on Red Hat 6. This is not entirely a disaster, because as long as you keep building on the oldest version that you care about, your GCC will be fine. And libc or glibc is written pretty well. And they use version symbols. So instead of a simple kind of So in your shared libraries, instead of a single saying this symbol name, this function call, they actually version their function calls. It's one of the fewer libraries, I guess, that do that properly. Which means that as you let's say keep developing, they don't have to break the entire library or the API every time. They can just say, okay, so this function now just has a different version, and there's 2 entries in your shared library for that function, and the old version keeps being built and keeps being available in the shared library. Which means that if you build on an old version, if you use a new libc because you've moved to a newer distribution, the old symbols are still going to be there, and it's just going to find the other direction still. But that's why you can deal with GCC being on your old system. It just means that your build host has to be the old system. That's one. What I've already said. The last thing, I have a few minutes left, I think, is basically when you're trying to build such an entire environment, you obviously end up with bootstrapping problems. Initially, you don't have Conda itself, you don't have your compiler itself, so you have to try to bootstrap this. Conda makes this, well, it's always good. It's not too bad. You kind of, there's a few particularity with Conda itself. It's basically, so initially you'll see you compile outside of your environment, you need to come outside of your environment to go to build commands. But once you've actually built your required components, you can start adding, you change they call the recipes, actually how to build specific package. You can start adding those dependencies in as you have them. But at some point, the one thing I would like to point out in this as well, so in the Zlib example, for example, Zlib is a very good entry point if you are trying to bootstrap an entire distribution. But Zlib, just GCC itself uses Zlib, so you end up, so you build everything until you can build GCC. And then you want to rebuild Zlib because you want to build Zlib with your own GCC. And there's one thing to look out for in Conda, because the Conda build system actually creates an environment for you with the directory with everything in place. And then it basically scans that entire environment and looks at all the files that exist. Then it will run your build system, which is basically configure and make install the case. And then it will scan again, and it will look at what new files are there, and those are the files that go into your package. Obviously, it said it was already a dependency, and it was already there in the first place, and you just overrode those files. So you have to be a little bit careful there with, you have to be a little bit careful there with, and you actually have to create an environment in an environment to work around that. But that's kind of one thing to be careful. I think I've used my time up. Thank you for listening.
Okay, do we have any questions?
Yes, please. You covered a lot of ground and talked about a lot of mechanisms that you want. Is it hard to use in practice? Is it a lot of work to get
to make a distribution yourself from scratch? It's a fair amount of work. It makes it as easy as possible. Once you the bootstrapping bit is hard. Once you bootstrapped it, it's easy. Making new packages after bootstrapping is really cool work figuring out.
Okay, Brad?
I didn't quite understand, when you bootstrap that environment, does libgcc get included in what you would distribute?
That is the reason we build GCC ourselves, because when you end up compiling C++ projects, you need libgcc to be linked in your C++ project. So you need that libgcc to be mapped with the matches on basically that you use that runtime. That is a little bit hacky as well. It's not terribly well supported, but basically we end up, the way we do that is we end up one package being GCC where all the GCC is in, but obviously at runtime you don't want all the GCC because it happens to be a C++ library that we just call it. we created the way to program it is by creating another Conda package that doesn't actually build anything. It just builds depends on GCC, pulls out libgcc, and then you have a package that just lots of few files. But then you end up with a small runtime package for libgcc basically. Is that a question?
I think so.
Any more questions?
So I want you to create a distribution like that. How will I apply to have for it? Like how many users come from it?
Not really. Yeah.
It seems to work. Each generalizes
All our test hosts, so we're in testing on Jenkins, currently for Red Hat and seems to work now because we haven't had anyone reporting.
How does this compare to containers?
I guess we actually use it in containers as well because we're already building it. If you're entirely doing it, if you can distribute using a container, but that means the user has to have a container runtime. This depends on nothing apart from your CV on the target environment, and that's the benefit. If you can distribute a container, it's probably easier because you can just configure that installed in your container, and you don't have to care about where it ends up. But this is like in one directory.
I understand the code. I don't know much about your product, but your product is something that plans install and it runs as a minion in the environment. So it has the non-dependent, so containers such as Nazca, something like
yeah, we want to be able to, we want people to be able to run, because it's an Asian balance to monitor, so wherever they happen to be, if they want to monitor inside a container, then we need to run in the container. If they want to run inside the VM, then we need to run inside the VM. So this kind of works wherever there is kind of a Unix system, and whether it's in a container, we don't, Conda doesn't actually care whether it's inside a container or outside.
So the package to use that distribution, does that end up being massive?
Yeah, reasonably. It's not small, but it's not huge. It's a couple of 100 megabytes. So the smallest you need for a working Conda, so Conda itself is written in Python. The smallest the smallest environment that you can just run Conda is, I think, 250-ish megabytes, something like that. But then you have fully functional standard library Python.
Lots of batteries. Lots of batteries.
Yeah.
That was pretty trigger.